12th.
कैसी प्रिपरेशन?
सर अच्छी जा रही.
ये चलेगा, अच्छी आ रही है। एटॉमिक स्ट्रक्चर में आप कंप्लीट दी एनसीईआरटी?
Pardon?
हैव यू कंप्लीटेड दी एनसीईआरटी एक्सरसाइजेस?
Sir nearly finished.
हम्म,
Nearly.
व्हाट अलीना? नियरली. हैव यू मार्क्ड एनी क्वेश्चंस इन व्हिच यू हैड डिफिकल्टी? हम्म, यस अली.
So can you repeat what you're speaking? Your voice is not clear.
How about now? Am I clear now?
Yes, sir.
Yeah. I was asking, have you noted down the questions in which you had difficulty in atomic structure?
Yes.
Yes. Okay.
Sir, question 2.9.
2.9. चलिए ठीक है, पूछिए आपकी. Very good. That is from the exercise, right?
Yes, sir.
In this chapter, you will have a lot of calculations, but you need to understand how to approximate things. ठीक है.
Okay, sir.
जब तक कोई बच्चा नहीं आ रहा तब तक आपको हम पढ़ा देते हैं. And when other students are joining, then you start with periodic tables, है ना? Where we ended. Photon of wavelength this much meters strikes on metal surface. The work function. The work function of metal being 2.13 electron volts. Calculate the energy of photon in electron volts. So this is the photon's wavelength. You have to calculate the energy in electron volts. The kinetic energy of the emission. Now in photoelectric effect, we know that when a metal is hit by photon, then electron is ejected with some kinetic energy. You have to calculate the kinetic energy, and then this kinetic energy will correspond to a certain velocity. You have to calculate the velocity. First of all, we are going to start with the energy of photon. So we know that energy, it is equal to h3 upon lambda, and we can use the formula energy, it is equal to 1240 upon lambda, where lambda will be in nanometers and energy will be in electron volts. Do you remember this formula at all?
Yes, sir.
You remember this formula? Very good then. So ठीक है. So lambda, it is given as 4 into 10 to the power minus 7 meters. Now I want to convert this to nanometers. That is why what I will do, I will write 10 to the power minus 9 meters. Okay. So what I have done here, tell me, -7 to -9, it is an increase or decrease? -7 to -9. I've
Decrease.
gone from decrease. How much? Two times, right?
Yes.
Correct? So this will become 400. If I am decreasing here, I have to increase the number, and this will become 400 nanometer. Now I can use that here, and I can write that energy is equal to 1240 divided by, this will be in electron volts. So 4, what? 3s are 12, and then 4 is going to come down, and you will get 4 ones are 31. The energy of the photon, it is equal to how much? 31 electron volts. Correct? Make sense, Alina?
Yes, sir.
Now, after that, you have to calculate the kinetic energy. We know that kinetic energy will be equal to the energy of photon minus the work function, or phi. Have I used the word phi in your case? I don't think so. No? Kinetic energy, we mostly use W as work function. No, we have used here W. Kinetic energy is equal to E minus W. Abhi, we are going to start. Alina had a doubt in atomic structure. Something like that. Energy, it is equal to 31 electron volt minus W. W is given as 2.13 electron volt. So this will be equal to how much? Tell me. Alina?
29.13 electron volts.
29 नहीं होगा ना, 28 होगा, राइट? 28.87. राइट? देखिए,
Sir, how you got it? I didn't understand.
oh my God. देखो, 31 माइनस 2 किया पहले हमने, दैट इज इक्वल टू 29. फिर इसमें हम क्या माइनस करेंगे? 0.13. So this will be equal to 28.87. First I
Okay, sir.
subtracted 2, then I said, oh, got it. Fine.
Yes,
Because
sir.
you were saying 29, no? It will not be 29 points because it is more than 2.2. 28.87, it is the kinetic energy. We need to calculate the velocity. So we know that half mv square, it is equal to kinetic energy. Kinetic energy, it is equal to 28.87. Okay? And mass is given, ना? Mass of electron डालना पड़ेगा फिर आपको. So we can write velocity square is equal to 2 times kinetic energy, 28.87, divided by mass of electron. Now we need to convert things. This is in electron volts. I will convert this into joule. 1.6 into 10 to the power minus 19. I think this has been given in the question. है ना? 1 electron volt is equal to 1.6 into 10 to the power minus 19 joule. Divided by the mass of electron, that is equal to how much? 9.1 into 10 to the power minus 31 kg. Fine. So what will be the velocity? देखिए, यहाँ पे आपको क्या मिल जाएगा ना? This part, this is what? This is joule. And what is joule? Joule is kg meter square per second square. So kg and kg will cancel each other, and you will get velocity square is equal to 2 into 28.87 into 1.6 divided by 9.1 multiplied by 10 to the power minus 19 plus 31. Now meter square plus second inverse minus 2. Now you need to do some calculations, or if possible, we will be doing some, what I say is some regard. 9 3 are 27. 3 to the 6 into 1.6 into 10 to the power how much? 10 to the power minus 19 plus 31. 21 and 12, I guess, right? Will be 12, right?
12
And
siblings.
6, 12, right?
So 12.
Uh, 6 into 1.6, very weirdly, but V square, I will write it 9. Multiply करके देखिए, it is approximately 9 only. A bit less than 9, but still 9. No, it will be a bit more than 9. Multiplied by 10 to the power 12. I have taken 9 because I have V square here. I can see that, so I have to be taking some number which is a perfect square, so I can have some easy calculations. And I can get an approximate answer. And I will get V will be equal to 3 into 10 to the power 6 meter per second. Can you check the answer? You have the answer in the NCERT textbook, right? At the back. I mean,
Yes.
obviously, it will not
It's
be exact, but it's right. The velocity and everything, is it exact? It should not be exact. Is it exact? No, no.
no. So
It's very far away. It's kind of far away. Right? Wait a second.
sir, it's 4.97 into 10 raised to power minus 19 joule.
And that is Joule, na? I don't want to worry. I have this value is not correct for us. Why is this value not correct? Oh my bad. देखिए कितनी बड़ी mistake हो गई. I have written here 400 nanometer. I have taken here 40. 400. It will be 3.1. It will be 2.87, I guess. It is okay. Now complete. I have no complete calculation. Okay, yes. I have calculated the energy wrong itself. वो जूल और एनर्जी छोड़ दीजिए. We have calculated this in electron volts ना. Electron volts will be 3.1 only. And yeah, पूरा हुआ पूरा. Energy minus. That is why we should not do anything in a hurry. How much? 1079. 0.97 electron volts. If you subtract this, this will be this many electron volts. Now I need to calculate the V square. Half mv square is equal to 0.97 electron volts. So एक बात देखिए, this is 3.1 only ना, Alina?
हाँ sir.
And kinetic energy is 0.97 electron volts. No. Sorry. Kinetic energy is 0.97 electron volts. Yes or no?
0.97.
97 people. 19 into 10 to the power minus 31. Yeah, that's it. 2 into 0.97 upon 9.1. We have to also multiply. 2 into 0.97 into 1.6 into 10 to the power minus 19 plus 31. Uh, that will be approximately 3 threes are. If you multiply these two numbers, it will be approximately 3. You can multiply it and you will see that. 2 into 1.6. ठीक है, it will be 3.23 के करीब आएगा. and 3.2 into 3, it will be approximately 9. So 3.2 into 0.97 divided by 9.1. Fine. So 3.2 into 0.97 will be a bit less than 3.2. So you can completely multiply like this, and this will be 1 by 3. Obviously, approximately speaking. Like CT का रहा है. Let me do a complete calculation. 9.1, 1.6, 0.97, 2 upon 9.1. 2 into 0.97 into 1.6 upon 9.1. What is the answer for velocity? Huh? This is coming as 0.34 for me. 0.34 multiplied by 10 to the power 12 v square. So v will be approximately, if I say, I can say this 34 into 10 to the power 10 and v square, and v will be approximately like 6 थोड़ा सा कम होगा 5.8 or 5.9 into 10 to the power minus 10 to the power 5 meter per second. This will be the velocity. 0.36 अगर होता, root of 36 will be I mean completely 6, but it is 34. Root of 34 will be 5.8 or 5.9, you can say. अच्छा, if you have more doubts ना अलीना, क्योंकि हमको लग रहा है आपने मार्क करके रखा है, तो please send it on my WhatsApp, okay? We can discuss that on over WhatsApp, right? चलिए, जल्दी जरा लिखिए. Moving on. By the way, we were talking about atomic radius. We did atomic radius. Now we are going to do ionic radius. Okay. So please write the heading ionic radius. Right. So we have two types of ions. We have two types of ions: anions and cations. How do we get anion? We have A in which we add electron and we get an anion A negative. We have a neutral atom A and we remove electron from here and we get a cation A positive. Fine. We remove one. Now, while you are removing the electron, what is happening? Let us suppose this A, it was initially holding some electron. Now the same number of protons, because we are not changing the protons, this is very important, please try to understand. We are not changing the number of protons, but in anions we are increasing the electrons. So the load on proton is very high now. Proton was able to hold, let us suppose there were 11 protons, so it was holding only 11 electrons. When you add one more electron, now the same 11 proton, they have to hold the 12 electrons. 11 proton has to hold 12 electrons. That's going to be difficult. That is why what's going to happen, when you add electron, the size increases because the proton is not able to hold, it does not have the capacity to hold that one extra electron. So what happens? This is the parent atom. Parent atom, its size is less than that of anion. But if I talk about cation, And in cation, we are removing electrons. So initially, if we had 11 protons and 11 electrons, right now we have only 10 electrons. And those 10 electrons will be very much attracted by the nucleus, and the proton will be effectively attracting them and getting them closer because of attraction. And that is why in this case, the size of parent atom is greater than that of cation. So in general, for an element, the size of an ion, the size of an ion is largest, followed by neutral, followed by cation. The cation is going to be smallest. A negative is largest. A is neutral, which is in the middle, and the smallest will be the A cation. For an element, है ना? If you are comparing in an element only, an ion parent cation is smaller than parent. Is everyone done? Anyone still writing? Done,
1 minute,
Alina?
sir.
Okay.
Done, sir.
नेक्स्ट लिखिएगा for isoelectronic species. For isoelectronic species. Isoelectronic species में क्या होगा? We are going to have same number of electrons, है ना? For example, N3 negative, O2 negative, F negative, fine. Similarly, sodium positive, magnesium 2 positive, aluminium 3 positive. If I talk about the atomic number for these cases, then atomic number it is how much? It is 10. No, it is 7, 8, 9, 11, 12, and 13. So if atomic number, it is going to talk about the number of protons, and the number of electrons is 10, 10, 10, 10, 10, and 10. So tell me, which element from these, from nitrogen to aluminium, which element is going to hold the 10 electrons most effectively? Which element is going to hold the 10 electrons most effectively? Alina, Abir, Ali, which element is going to hold the 10 electrons most effectively? जल्दी बताओ.
And
Night, yeah, aluminium, right? Because aluminium is having 13
yes.
protons. So 13 protons will be very effectively holding those electrons and making it closer to the nucleus. And that is why its size will be smallest. So the size order is like this. And for isoelectronic species, we can say that size, it is directly proportional to the negative charge. Larger the negative charge, larger will be the size, and it is inversely proportional to positive charge. Waiting for Alina and Ali. All of you understood this thing? Yes or no? Please let me know. ठीक है यार चलिए. अच्छा इन जनरल वन की दिस फॉर आइसोइलेक्ट्रॉनिक स्पीशीज और वास्ते आप समझ लीजिए. If I go across the period, then ionic size, in general speaking, ionic size decreases, and if I go like this, then ionic size increases. Fine. Across the period. In general यही properties है. Fine. Now after that isoelectronic species का एक केस अलग आ जाता है. Now we are going to do a few examples. उसके बाद फिर हम लोग आगे बढ़ेंगे. Compare the ionic radius of following. ठीक है. For example, you have oxygen 2 negative, sulfur 2 negative, fluorine negative, fluorine negative. ठीक है. As soon as you get this now, what you need to do is you need to arrange these elements in the periodic table according to the periodic table. So we know that we have oxygen, after that we have fluorine, below oxygen we have sulfur, and below fluorine we have fluorine. So this is 2 negative, this is 2 negative, this is negative, and this is negative. First of all, you have to see like what is common between them. Charges is never common. And two negative charge, please don't say that is common. Either the period will be same, or the group will be same, or it will be an isoelectronic species. Then only we can talk about, okay, fine, these things are same. So if I look at the sulfur and fluorine, then it is going to be the third period elements. And oxygen and fluorine are second period elements. So obviously, we can say that what are the things that we can for sure say? We can say that O2 negative is obviously going to be smaller than sulfur 2 negative because it is having 3 shells. Oxygen is having only 2 shells. Similarly, I can say fluorine negative will be obviously smaller than chlorine negative because chlorine negative is having 3 shells and fluorine negative is having only 2 shells. Now, next is what we can say regarding oxygen and fluorine is that oxygen will be larger than fluorine. Why? Because right now we have already seen oxygen is having 8 protons, fluorine is having 9 protons. Both of them are having 10 electrons. That is why it will be easier for fluorine to hold those 10 electrons rather than oxygen with the 8 protons. Another thing, in the very same fashion, we can say that sulfur 2 negative will be greater than fluorine negative because that too also will be an isoelectronic species. Both of them will be having 18 electrons. Now, these are the some orders that we can say for sure. Then now what you can do is you can compare. Now you can see that fluorine is always smaller. Whether we are talking about oxygen or we are talking about fluorine, it is always smaller. Fine. So fluorine is going to be the smallest one. See, if I first of all, if I see oxygen is smaller than sulfur, fluorine is smaller than fluorine, and fluorine is even smaller than oxygen, so obviously it is going to be smaller than sulfur. Now, please remember, after fluorine, now you have to think about oxygen. It will be oxygen or what? Fine, oxygen or fluorine, because fluorine is smaller than sulfur, and oxygen is also smaller than sulfur. Then you have to think about the shell. Oxygen is having 2 shells. Sulfur is having 3 shells. So obviously, oxygen is going to be smaller than O2 negative. Fine. After that, we are going to have fluorine negative, and the largest size will be of sulfur 2 negative. So this is the order. What is the deciding factor between these two? The Z upon E ratio. Fluorine has higher amount of proton. That is why it is going to be having smaller size. Oxygen is having less. Oxygen is having less proton and it is having more electron. That's why its size is greater. Hai na? Fluorine size is smaller. Next, what is the deciding factor between oxygen and fluorine? It is the shell number or the period number, you can say. Period number. Oxygen is in lower period, that is why it is having small size. Fluorine is in higher period, that is why it is having larger size. Between fluorine and sulfur, again, the Z upon E ratio of fluorine was greater, that is why its size is smaller, and sulfur was having less number of proton as compared to chlorine, but it had equal number of electron as compared to chlorine. That is why it is having larger size. It has less number of protons. Okay, copy this down. Raise your hand once you're done. Raise your hand once you're done. Is everyone done? Waiting for Alina.
You're done.
Done. You have not raised your hand.
Sorry, sir.
Sawal. Compare the signs. Oh, wait a second. Hmm. Compare the signs for following. I negative, I positive, and iodine. This is A, this is B, this is C. First option is A is greater than B, it is greater than C. Second option is A is greater than C, it is greater than B. Third option is B is greater than C, it is greater than A. And fourth option is C, it is greater than B, it is greater than A. Okay, we are waiting for Alina and Ali. Waiting for Alina and Ali. अलीना आपको आ रहा है? अलीना
Yes, sir.
आंसर दीजिए.
Sir, I'm confused.
अली अली आंसर बताइए. अली आंसर बताइए. अली इज नॉट हियर और व्हाट? अबीर एक्सप्लेन मी द आंसर. अबीर एक्सप्लेन मी द आंसर.
Yes.
जी बताइए. एक्सप्लेन इट टू मी.
Sir, the anion is always greater than the neutral atom or the parent atom, and then the neutral one is always greater than cation. So the
You have studied
answer,
this? आई नेगेटिव सबसे ज्यादा होगा, उसके बाद आई होगा, उसके बाद आई पॉजिटिव होगा, है कि नहीं? अभी इतना आसान था, क्या कंफ्यूजन
Yes,
थी
sir.
इसमें अली ना? दिस इज ए, दिस इज सी, दिस इज बी, सेकंड ऑप्शन। अलीना एंड अली, ये इतने आसान सवाल नहीं होंगे आपसे। कहाँ ध्यान है? आपको जल्दी छापो। जस्ट वेटिंग फॉर अली। नेक्स्ट हेडिंग डालिए, आयोनाइजेशन एंथैल्पी। ठीक है, डेल्टा एच आई ई और डेल्टा एच आई, आयोनाइजेशन एंथैल्पी। So please write the energy required to remove energy required to remove most loosely bound electron from a neutral isolated gaseous atom. From a neutral isolated gaseous atom. Okay. Now, why do we take this neutral isolated gaseous atom? This is a question in NCERT. Why do we take this? What is the importance? What is the significance? This is for uniformity of comparison, for uniformity of comparison, and 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 for uniformity of comparison and इतना ही लिख लीजिए, इसका मतलब समझा देते हैं, तो लिखाने में बहुत ज्यादा लिखा देंगे। ठीक है, ठीक। If I don't take, what is the meaning of neutral isolated gases atom? We have only one atom, okay, in which we have some proton, and that proton is the only one which is attracting the electron. That proton is the only one which is attracting the electron. If I have a neutral isolated, that means it is individual and atom. But if I take something which is, for example, solid, the metal, the complete thing will be completely packed. So these are the nuclei, and there will be electrons here. Fine. Now, I'm showing the red as the electron of this atom and the blue as electron of this the other atom. Right? Now we know that if I want to remove the if I want to remove the red electron, right now the red electron is also attracted by this proton and the adjacent proton. Both the nucleus are quite closer to the electron, and both of them are going to have certain attraction. Fine. Also, the blue electron will be repelling the red electron. The blue electron will be repelling the red electron. Now, this type of complexity, it occurs when we don't take a neutral isolated gas system. And this type of complexity will not be similar for each type of element. The attraction by the two protons will be different for carbon, and it will be different for iron. The repulsion in electrons will be different for carbon, it will be different for scandium, sodium, and fluorine, and all of these other elements. That is why we take such an atom, a neutral isolated gaseous atom, so that the only attractive force which is present for the electron is the nucleus of that atom only. And that is why we will have some kind of uniformity, and we can compare the different types of different ionization enthalpies of elements. Right? So this is the meaning of ionization enthalpy. The energy required to remove most loosely bound electron from a neutral isolated gaseous atom. Now another part is delta H I is defined for 1 mole of electron. Okay. So if I remove an electron, if I remove 1 mole of electron from not 1 mole of atoms, but 1 mole of atoms, or 1 mole of atoms, है ना? Okay, so if I take 1 mole of this type of atoms, then that energy is known as the ionization enthalpy. Fine. That energy is known as ionization enthalpy. It is measured in 1 mole of atom. Kilojoule per mole में इसका unit होता है. ठीक है. That we are going to learn more in more details in the thermodynamics. Now, another part is, since energy is required to remove electrons. Why do we require? Why does it require energy to remove electron? Because we have to break the attraction of nucleus and the electron. Required to remove electron for ionization. The process is endothermic. That means it will require energy. That means the system, the atom is going to require energy. We have to give energy to the system. That will lead to a positive change in enthalpy. That is why delta H is always positive. Delta H is always positive because we have to give energy to the system. And when you are giving energy to the system, the energy of the system is going to increase. And when something increases, that change is what? That change is positive. Pop it down. Raise your hand once you are done. Just waiting for Ali. See here. Let us suppose we have some element M and you are going to remove an electron. So it will give you M positive. Right? This is known as first ionization enthalpy. Or you can say in short, IE1 of M. But when you remove electron from M positive, it will give you M2 positive. This is the second ionization enthalpy of M, or first ionization enthalpy of M positive. Both of these are the same thing. Second ionization enthalpy, yeah, that it means that you're removing the second most loosely bound electron. The most loosely bound electron is first ionization enthalpy, it means that you are removing the first most loosely bound electron from the metal or any element. Second ionization enthalpy of material means you have removed one electron, the second most loosely bound electron will be removed now. Okay, but if I talk about M positive, then from M positive we are removing the first most loosely bound electron. If you are going from M2 positive to M3 positive, then I can say that this particular process, by the way, it is going to give you one electron, it's also going to give you one electron, this is also going to give you one electron, right? This means we are removing the third most loosely bound electron of metal, of element M, or the second most loosely bound electron of M positive, or the first most loosely bound electron of M2 positive. Does this make sense? Yes or no, please tell me.
Yes, sir.
Copy this down, raise your hand once you're done. Raise your hand once you're done. Also, right, next point. This is known as successive ionization enthalpy, and hopefully, I hope you can understand that the removal of the first electron will be the easiest when compared to the successive ionization enthalpy, because once we remove one electron, we are going to have less electrons, and the proton will be still the same. So those protons will be attracting the electrons more effectively. If you remove one more electron, then the proton will be still the same. Electron has been reduced even more. Pull from the nucleus will be even more high if you have removed two electrons and so on. So the successive ionization enthalpy, it is always higher and keeps on increasing. So we can see from in this point that for M, the first ionization enthalpy, it is the smallest. The removal of second electron, it is tougher than the first, followed by the third ionization enthalpy, and so on. Successive ionization enthalpy keeps on increasing. of this round, raise your hand once you're done. अच्छा इसमें क्या ही raise hand कराएगा मतलब. So looking at factors affecting ionization energy or ionization enthalpy. Factors affecting ionization energy. ठीक है, ध्यान से देखिए. Number one, size of atom. Right? So if the size will be higher, then what is going to happen? It will be easier to remove. The size is higher, electron is far away. Easier to remove electron. So we can say that ionization energy, it is inversely proportional to size. Size increases, ionization enthalpy decreases. Second, Z effective. When the Z effective will increase, Z effective increases, attraction increases, and it is difficult to remove electron. So we can see that ionization enthalpy, it is directly proportional to Z effective. Because if it is difficult to remove electron, it will require higher energy. Third is penetration power. Meaning the electron in S subshell will be difficult to remove compared to P subshell, compared to D subshell, and compared to F subshell. Okay. But when we are in the same shell, if we are in the different shell, then size is going to matter most. But if you are in the same shell, the size is same. If you are in the second shell, then that's why I'm writing NS, NP, ND, and NS. Fine. When you are in the same shell, then we have to compare. If you are on a different shell, then we don't compare this NS and P. Okay, you have to have the N should be same. You have to compare 2S with 2P. You cannot compare. You cannot compare PS with 2P. When I compare 2S with 2P, it will be difficult to remove electron from 2S. But if I compare from PS and 2P, then it will be difficult to remove electron from 2P. Why? Because it is in the second shell. This is the third shell. Fine. So when you are having larger shell, obviously it will be difficult to remove from the smaller shell. But if you are having the same shell, then you have to look at the subshell. The last one is stable electronic configuration will have higher ionization enthalpy, such as half filled, fully filled, and noble gases. Why does this would require higher ionization enthalpy? Because if any particular electronic configuration is stable, then the element will not like any disturbance in the electron, because that configuration is stable. If it is half filled, element will not accept any disturbance. That is why it will be very difficult to remove the electron from half filled, fully filled, and noble gas, because they are having the stable electronic configuration. Makes sense, everyone, till now? Yes or no? Please tell me. Alina, Abir, and Ali. Yes or no, guys?
Yes, sir.
Yes, sir.
जल्दी जल्दी कॉपी कीजिए जल्दी. Waiting for Alina and Ali. Waiting for Alina. Right next, general trends for ionization energy or ionization enthalpy. चलिए बोलिए. Across the period, what happens to Z effective? बोलो. Z effective, it increases, decreases, is constant across the period. बोलो भाई. Z effective is what? हाँ अभी जोर से बोलो. Z effective increases, decreases, or it is constant across the period.
Same, it
पढ़
is
के.
constant.
It is constant. It increases. It's constant. Size. Size. बोलो. What happens to size across a period? कुछ नहीं पढ़ के आए. आज ही कराया मतलब लास्ट टाइम तो कराया साइज भाई. हाँ. व्हाट हैपेंस टू साइज अक्रॉस अ पीरियड भाई? एटलीस्ट नोटबुक देख के तो बताइए आप लोग. क्या है भाई, कुछ पढ़ वढ़ के नहीं आते हैं? हाँ. साइज डिक्रीजेस. effective nuclear charge is increasing, size is decreasing, so ionization enthalpy. बोलो.
Increases.
Very good. It will increase from top to bottom in a group. चलिए. Z effective. बोलो. Z effective
Increases.
is constant. It's constant. Size बोलो size. बोलो. Top to bottom in a group. Size.
Increases.
Hmm. Size. बोलो. Come on,
Increases.
Alina. You have to. I mean, you have to
Decrease.
read. Na. बोलो. Size increases. Ionization enthalpy. Size increases. So ionization enthalpy.
Decrease. Decreases.
What? कर रहे हैं. Decreases. Very good. This is a general trend for ionization enthalpy. Now we are going to see some irregularities. Exceptions. I hope you are done writing. Write the first exception. Ionization enthalpy of ionization enthalpy of second and third period elements. What happens here? See, if I am going to look at the second period element, then it is going to be lithium. Then lithium के बाद बोलो बेरिलियम. बोलो. बोलो भाई. lithium बेरिलियम. After that, किसी को नहीं याद है? No one remembers. Lithium, beryllium. What comes after beryllium? Abir, Alina, and Ali. बोलो भाई. Very sad.
Boron.
बोरॉन पूरा माइक ऑन करके कंप्लीट कीजिए ना. बोरॉन करके चुप हो जा रहे हैं. Say it. Boron, carbon, and then
Nitrogen.
nitrogen. Then mic on रखो भाई. Mic on रखो. Nitrogen. Then
Oxygen.
mic off हो जा रहा है तुरंत. क्यों गुस्सा दिलाना चाह रहे हैं? क्या पता है, अब माइक नहीं ऑन होगा. कुछ नहीं बोलना, किसी से कुछ नहीं पूछेंगे. माइक ऑन करके बोल. It is expected that it should be this order because the ionization enthalpy it increases across the period, but it is not going to be this order because we should look at the electronic configuration. Lithium will be having electronic configuration 2s1, this will be having 2s2, 2p1, 2p2, 2p3, 2p4, 2p5, 2p5 and 2p6. Now, when I look at the second shell and I compare beryllium and boron, then in beryllium we are having the electron in the s subshell, but in boron we are having in the p subshell. That is why this order is incorrect. S subshell will have higher penetration power, and that is why it will be having higher ionization enthalpy. The order is okay till nitrogen, and in nitrogen we have 3 electrons, 2p3 which is half filled and 2p4 which is not half filled. That is why this configuration is also wrong. In this case, oxygen will not have higher ionization enthalpy, nitrogen will have higher ionization enthalpy. So the order becomes lithium, not beryllium, but rather boron, and after boron we have beryllium, and then we have carbon, not nitrogen, but carbon, not nitrogen, but oxygen will have smaller and nitrogen will have larger. After that, we are going to have fluorine, and then we are going to have neon. Fluorine and neon. The reason in the case of this is the correct order, actual order. The reason here is penetration power, and the reason here is half filled 2p3. Similar is the order for third period elements also. We have sodium, then we don't have magnesium, we rather have aluminium, then we have magnesium, then we have silicon, and after then we have sulfur, then we have phosphorus, and then we have chlorine, and then we have argon. By the way, this will be having minimum because if I remove this one electron, it will reach the noble gas configuration, and this will be maximum because it is already noble gas configuration and it does not want any disturbance in the electronic configuration. So this is the order. Again, here the reason is penetration power, and between sulfur and phosphorus, it is the half filled of phosphorus. Copy this down. Raise your hand once you're done. Copy this down. Raise your hand once you're done. When I ask something, I either you have to say, sir, I don't know, I cannot say, I don't remember the periodic table, or you answer things. है ना, नहीं करेंगे तो हम ऐसे ही पढ़ाएंगे, कुछ नहीं समझाएंगे हम. Raise your hand once you're done. Waiting for Alina and Ali. When I say keep your mic on, you don't keep your mic on. You use the space bars. Very good. एक तरफ से कोई ना कुछ होता है, इतनी इतना अच्छे से आराम से प्यार से पढ़ाते हैं, कुछ नहीं मतलब आप लोग. Raise your hand. Quickly raise your hand. In general, we can say that any uh, any element with configuration ns1, if I want to compare in a particular period, then we can say that ns1 will be having the least ionization enthalpy, followed by np1, followed by ns2, followed by np2, followed by np4, then np3, then np5, and then np6. This is valid for first ionization enthalpy, second ionization enthalpy, etc. Compare second ionization enthalpy of carbon, nitrogen, oxygen, and fluorine. We have carbon, nitrogen, oxygen, and fluorine. Electronic configuration, the outermost electronic configuration of carbon is 2s2. Sorry, not 2s2, 2p2. 2p2. For nitrogen, it is 2p3. For oxygen, it is 2p4. For fluorine, it is 2p5. Because we are going to calculate the second ionization enthalpy, we have already removed one electron. We have to see from where we have to see from 2p1, 2p2. This will be 2p3, and this will be 2p4. How difficult how difficult is it to remove 2p1 electron compared to 2p2, compared to 2p3, and compared to 2p4? If you look at all of these, then you can perfectly say that 2p3 will be requiring the highest energy because it's half filled. So you can say that oxygen, second ionization enthalpy of oxygen will be highest. Now followed by the lowest start collector. Lowest will be 2p1, as you can see, np1, then np2, right? So 2p1 will be the lowest, meaning carbon will be the lowest, followed by 2p2, that is nitrogen, followed by 2p4, that is fluorine, and then followed by 2p3, that is oxygen. If I similarly compare the second ionization enthalpy, second ionization enthalpy of sodium, magnesium, sodium, magnesium, aluminium, and silicon. And here also you have to do the same concept: sodium, magnesium, aluminium, silicon. Now in this case, sodium it is having 3s1 configuration, this is having 3s2, this is having 3p1, and this is having 3p2. But then since we are going to remove one electron and see, because it is the second ionization enthalpy, you have to see the lowest, most loosely bound electron, second most loosely bound electron. When you remove one electron from PS1, the outermost electronic configuration, it becomes 2p6. Because before PS1, we have 2p6, which is now 2p6 is going to be a noble gas configuration. Then we have PS1, then we have CP1, if you remove one electron, PS1, this will become PS2, and this will become 3p1. Now, if I compare the electronic configuration, then obviously the PS1 will be the smallest, like Mg will be having the smallest, followed by between 3s2 and 3p1. Obviously, 3p1 will be easier to remove electron because it's p substance. That is, it will be silicon, and after that, we are going to have aluminium. And the largest will be for sodium right now. Why? Because sodium, when you are removing the second most loosely bound electron, it has already achieved the noble gas configuration. And because it has achieved the noble gas configuration, it will be requiring the maximum ionization energy. Copy this down, raise your hand once you're done. Compare first ionization enthalpy and second ionization enthalpy of lithium and beryllium. And similar will be the case of, and similar is the case of, similarly, sodium and magnesium will be also having similar case. So for first ionization enthalpy of lithium, I have to go from lithium to lithium positive. Lithium, it is having an electronic configuration of 2s1. Right now, lithium positive, it is having an electronic configuration of 1s2. So 2s1 say 1s2, and first ionization enthalpy of lithium. And for beryllium, if I want to, same thing, beryllium to beryllium positive. So beryllium, it is having electronic configuration of 2s2. It's going from 2s2 to 2s1. Right? So obviously, we can say that since lithium is going from 2s1 to 1s2, which is a noble gas configuration, lithium's first ionization enthalpy will be smaller than that of beryllium. Right? Because beryllium is obviously having more number of protons, its effective nuclear charge will be higher, and it comes after lithium, right? So lithium, and then you have beryllium. Across a period, the ionization enthalpy is obviously going to increase. That is why beryllium is going to have higher ionization enthalpy than lithium. But if I compare the second ionization enthalpy of lithium, that means I am going from lithium positive to lithium 2 positive. Then I am removing electrons from the 1s2 configuration and doing it 1s1. This will require a very high energy because it is very stable. 1s2 is very stable. If I do the same thing for beryllium positive and I go to beryllium 2 positive, then in this case I am going from 2s1 to 1s2. Right? Obviously, this is going to require a larger amount of energy, but it is going to be lesser than that of lithium. Why? Second ionization enthalpy of second ionization enthalpy. Right? Now, I can say that in this case, the lithium will be having higher ionization enthalpy than beryllium. Why? Because due to stable 1s2 configuration of lithium positive. Since lithium positive, it has a configuration of 1s2, which is very stable. It is a noble gas-like configuration. It will be very difficult to remove electron from the lithium positive. That is why the second ionization enthalpy of lithium it is greater than the second ionization enthalpy of beryllium. But if I compare the ionization enthalpy of lithium and beryllium, which is the first ionization enthalpy, then it follows the general trend that beryllium is going to have a higher ionization enthalpy than that of lithium. Up it is down, raise your hand once you're done. Similarly, there is a question in NCERT for sodium and magnesium. बिल्कुल similarly आपको करना है. You don't have to do anything. You can say that why beryllium is having large ionization enthalpy. This is due to higher Z effective and smaller size of beryllium. Copy this down, raise your hand once you're done. Just waiting for Alina. लास्ट टाइम आप लोग को irregularities में क्या क्या भाग गया था भाई. Okay, everyone's done. Then write in boron family. You have seen the irregularities in the second and third period elements. B part in boron family. So the expected order is, as we are moving top to bottom in a group, we are expecting that boron will have the highest ionization enthalpy, followed by aluminium, followed by gallium, followed by indium and thallium. But the actual order, it is something like this. In order to remember this, you can use this mnemonic. You can write a stylish W. Fine. What is this stylish W? Please see. Here you have boron. Aluminium is having lower than that of boron, but gallium it is having higher ionization enthalpy, slightly higher than that of aluminium, and indium is quite low. And thallium we were expecting it to be low, but it is quite high. Although it is lower than that of boron, but it is still higher than that of indium and gallium. Now, how can we explain the irregularity in gallium? We can explain it by the poor shielding. Ionization enthalpy is high due to small size and high Z effective. Why the size is small and the Z effective is high? Due to poor shielding of 3d10 electrons. Now, when we go to thallium, in this case, there is a special phenomena that happens. We are going to that ionization enthalpy is high due to what we say lanthanide contraction. What is the meaning of lanthanide contraction? It is just meaning uh, due to, we can write one more, due to poor shielding of 4f14 electrons. So the actual order is going to be boron is going to have the highest, followed by thallium, followed by gallium, followed by aluminium, and the smallest will be indium. Copy this down. Raise your hand once you're done. Copy this down. Raise your hand once you're done. Waiting for Abir and Alina.